Hi everyone, my name is Joydas Burako. Currently I am doing PhD in IIT Kanpur in complex system. So from today onwards I will take a short course on testing of statistical hypothesis. So let me write it, testing of statistical hypothesis. So let me first tell you why I am motivated to do so, because since I am doing research on complex system, and while do so, in every time I face some problem. Suppose I want to make a computational model or theoretical model of a realistic system, and which is complex for it is complex because of different reasons. And since it is complex, the data that we get from the experiment is random in principle. And when I want to make a model of that random data or that output that I get from the experiment, I also generate by computer simulation or theoretical prediction some random data. Now if I want to measure that whether my randomly generated data is mimicking the actual experiment on the real world, I need some kind of test to test that whether whatever I am telling theoretically or whether I am telling by computer simulation, is it is it right, that we can we can say without error that my model is actually the model of the system, or my model is closely matches with the experimental system. To do so, we have to know how to test our hypothesis that our generated data is actually mimicking the real world experimental data. So to do so, we know the testing of hypothesis, statistical hypothesis. So what is that? So here we test a statement or an assumption about the in general probability distribution of a random variable. In case of my research, I have to guess or I have to make an assumption about a probability distribution from which the data is generated in experiment. So that's it. And we always have to clear in our mind that every things we do in model they actually are not the truth things, or they are rather, you can say like that, they are closest model of the simulation. So now let me give an example, realistic example, from where you can grab the matter clearly. That is, suppose there is a brand new there is a brand of drug for a certain disease. And from the experience, we know that the proportion of patients who get cured using this drug is 0.5. Now a new drug is invented and it is to be tried. Now you see, if a new drug is being introduced in the market or introduced in the medical science, then we have to check that does this new drug is more efficient than the previous drug or not. So to do so, we have to do a test. So now we will make a assumption that suppose this drug is better than the previous available drug in the market. So that means we have to make an assumption that and we will check that assumption, that the assumption is here. We have to make assumption that P is, suppose that P is the probability, and I assume that everyone in this course is familiar with the probability mean median. I am not gonna introduce those concepts in this course because I make this course very short, and I only focus on the testing of a hypothesis. So that's my goal. So I think you know the what I assume that you, this is again my another assumption that all of the students know the meaning of the probability. So here the P is the probability of patient who get cured after using the new drug. Now here then our assumption will be that P is greater than 0.05. Then we can safely say that the new drug is more effective than the previous available one. So here in this case we will test whether this assumption is true or not, and if it is true, then how much error we will do by assuming this is true, or if it is not, if it is not, then how much error we will make while saying it is not. So that's kind of thing. Another, give me another example here. So suppose we have measured we have measurement newborn child in an ethnic group. We want to measure what distribution these weights follows. So if you want to measure, so here we gonna make an assumption that the distribution is a normal distribution with some mean and standard deviation. This is our assumption here. This is our assumption of statement that we are going to test here. So that's how we make we first observe from the observation or nature or the world, then we assume, or then we make a model, or then we assume a distribution, then make a something like that in computer simulation, and we get another data set, and whether these two data sets are matching or not, then we compare and then we test. So this is we will do in this course, and this is we actually do in most of the cases. As you see, it is a useful tool for testing hypothesis in medicines and research in the every areas of these every area of the science. So now let me introduce what are the terminologies used in this subject. So first terminology is called null hypothesis and alternative hypothesis. Null and alternative hypothesis. Null and alternative hypothesis. Suppose let me give an example where what is the null hypothesis is and what is alternative hypothesis is, then it will be cleared. So suppose in a coin tossing experiments, we want to test whether the coin is fair or not. So now if we want to measure, and you see that these coin tossing experiment in principle are random variable. So the in principle the random is there in a coin toss experiment. So here how can we tell that the coin is fair or unfair? So here we gonna use the thing that let P denote the probability of occurrence occurrence of head, now then we want to test whether the coin is fair. Fair means whether the probability is p equal to half or p not equal to half. So this assumption or this statement we call the null hypothesis. Null hypothesis, and this assumption we call it alternative hypothesis. Alternative hypothesis. So we write here, we write in technical term like this: H0, this is alternative hypothesis defined as probability is half, and this is null hypothesis is defined as p equal to half, and alternative hypothesis is p not equal to half. Or you can this can also be a hypothesis, that null hypothesis is half and alternative hypothesis is, this is H1, alternative hypothesis is p equal to 1 by 4. This is also this is also can be the setting, this is also be a case. Now here we only focus on the null hypothesis. Here we want to test the null hypothesis. In a hypothesis testing, although there is a alternative hypothesis, but our main focus on the null hypothesis, always be on the null hypothesis. So the null hypothesis is a hypothesis which is tested for possible rejection under the assumption that it is true. So always our focus on will be on the hypothesis, null hypothesis, and we tested whether we can reject the null hypothesis or not. So suppose that in our data set, suppose that we toss a coin 4 times, suppose one head, one tail, one head and another head is the outcomes of this 4 coin toss experiment. Now from this data, can we reject the null hypothesis, that is p equal to half or not? So that will be our main motto. So what is the null what we will do here? We will assume as if the null hypothesis is true, that means as if the probability is p equal to half. Now we calculate what is the probability that our suppose that we will say that this coin is unfair if suppose number of head is greater than or equal to 2. Suppose these things, if this thing is true, then we will say the coin is a fair coin. Now we will calculate what is the probability that what is the probability that if our assumption is true, that coin is fair, then what is the probability that we can reject this hypothesis. So that is the thing. So in a hypothesis testing, we always our focus will be always on the null hypothesis, and whether or not we can reject the null hypothesis or not. So that is the thing. Now another thing we have to know is a simple, what is called a simple hypothesis, simple hypothesis, and complex hypothesis, and composite hypothesis. So in a simple hypothesis, suppose our hypothesis is such that the probability distribution of the process is clear. So suppose that our hypothesis is I am giving, so let me write it first. If a hypothesis completely specifies the probability density function, probability density function, then it is called simple, and otherwise the hypothesis is called composite hypothesis. So if our hypothesis does not specifies the probability distribution of the function, probability distribution function of the process, then we will call it a composite hypothesis. So let me give an example. So suppose x1, xn, these n random variables follows the normal distribution with mu and sigma square. Now if we know sigma, if we know the standard deviation, then these hypotheses, suppose our null hypothesis is mu0 is 0 and h1 mu1 is equal to 1. Since if we know the standard deviation, and if our hypothesis is such that mean is 0 or 1, that means that means from our hypothesis we can completely specify the probability distribution, then we will call these two hypotheses simple hypothesis. Now suppose that we don't know sigma, if we don't know sigma, then if our hypothesis is this, that h0 is mu0 equal to 0 and h1 is mu1 equal to 1, then this is called composite hypothesis. And this is also be a simple hypothesis, that is, suppose h0 star at mu0 is 0 and sigma equal to 1, and h1 star is mu0 is 1, sigma is 1. This is also a simple hypothesis. It's composite hypothesis. This is composite hypothesis. So that's it. So actually why I am introducing these things, because to test a hypothesis we have to know whether it is a simple hypothesis or not. So in the when I go further in this course, we will show that for the simple hypothesis there is a test, or there is a fundamental lemma called Neyman-Pearson lemma. By using that lemma we are very simply we gonna test a hypothesis, the most efficient hypothesis, most efficient test. So that's it. So that's why we need these concepts: simple hypothesis versus complex composite hypothesis. Now another things I want to introduce here, so that is called critical that is a critical or acceptance critical or acceptance region. So this is again a definition, so I have to means we have to know these definitions. So let me give you, so let S be the sample space of the random experiment. Now a critical region or a rejection region of the test is that part of the sample space corresponds to the rejection of the null hypothesis. So don't worry, this is a definition, so we don't need these things very much, but you have to know what is called the critical or acceptance region, because in the literature you will find this term very often. So that's why I am introducing this definition, that what is called a critical region. So basically critical region is that suppose that so let me give an example. Yeah, okay, example is here. So let me first introduce the whole definition, then I will give an example. So null hypothesis. So suppose that in mathematical term, if x belongs to SR such that we reject H0, then SR, suppose the whole sample space is S and SR is a subset of S, then SR is called rejection or critical region. Critical region. And the complementary of this S or C is called acceptance region. Acceptance region. So let me give an example. Suppose that so we have a coin, we toss it 3 times to test whether the probability of head is 1/4 or 3/4. Now suppose here our sample space is this 3 head, 2 head, 1 tail, head, tail, head, tail, head, 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 tail, 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 head, tail, and tail, tail, head, or tail, tail, tail. And here our hypothesis, the null hypothesis is P equal to 1/4, and alternative hypothesis is what? P is equal to 3/4. P is 3/4. So suppose that if A is equal to 1/4 means the chance of getting head in a 3 times tossing experiment is very less. So that means if the number of head is 1 or less than that, we gonna accept the null hypothesis. So that means we'll say that when we'll accept the null hypothesis, when what will be the acceptance region? So let me write it. We are going to accept the null hypothesis if the number of heads is less than or equal to 1. So then what is our acceptance set or acceptance region? That is the outcomes which contains only one head or no head. So that will be this, sorry, not this, that will be this, and this 4. The head, tail, 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 head, tail, 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 head, tail, 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 and the rest of them will be the rejection region. So that is head, 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 and head, head, tail, head, tail, head, and tail, head, head. So that is the thing. So that is the thing. Now another things we will I gonna introduce here, that is the as I introduce this subject, in the first I told you what kind of error we will do when we accept a hypothesis. That is the main issue here. So suppose that for example, suppose we accept this our null hypothesis. So if we accept the null hypothesis, what kinds of error are possible if we accept the null hypothesis? So that kinds of error is the main thing that we have to reduce while testing a hypothesis. So let me introduce what kinds of errors are possible, what kinds of exhaustive error are possible in these subjects. So in this subject, so there are two kinds of errors. So there are two types of error are possible in these subjects. Two types of errors. So this is a very important concept, and from the now onward we will talk in terms of these errors, and we will see what are the possible methods in such way we actually reduce these errors. And less error means our hypothesis testing is more powerful. So let's see it, what kinds of error possible. So when we conduct a test of hypothesis, we are likely to make two types of error, two types of errors. So first one is type 1 error, type 1 error. So that is reject the null hypothesis that is H0 when it is true. So these can be a error. So when the null hypothesis is true, in spite of that we actually reject the null hypothesis. So that is the error type 1 or the type 1 error, or this is called the first kind of error, error of first kind, error first kind. And another error which is independent of the type 1 error, so type 2 error is what is that? That is accepting. So it is the opposite of the first one, but there is a subtle difference. Accepting H0 when it is false. This is error of second kind. At first you will see this is the this is just opposite of that. That means if we can calculate the probability of that, then 1 minus of this probability is the type 2 error, but it is not true. You say the first thing is reject the hypothesis when it is true, and here the when the actual system follows the null hypothesis, follows the probability distribution that is mentioned by the null hypothesis. And in the second case, the actual system follows the probability distribution of the alternative hypothesis. So that means two systems are in principle are different. One, in the first type of error, the system is actually follows the probability distribution that we assume in the null hypothesis, and in the second type of error, the system is following the probability distribution that is mentioned in the alternative hypothesis. So between these two errors there is a big difference, so they are not complementary of each other. So that's it. So these two are independent error. So let me give an example. So let me so what is the best kind of test? What will be the best test? So the test which reduce these both type of error, that will be the base test. Now here alpha, suppose alpha is the probability of type 1 error, and so beta is the probability type 2 error. Now you see that if we make a test such that these both errors are minimized, then the test is called the most desirable test, because in that test we make minimum amount of mistakes. So that is our goal in these subjects, how to find that kind of test. But very sadly, so this test is not possible. We can't reduce the both kinds of error. You see, when you want to reduce the first kind of error, the second kind of error will be automatically be higher. Let's see that. So if you want to reduce the first kind of error, that means you actually going to reduce the rejection of the null hypothesis, and automatically if you rejection of the null hypothesis becomes very low, your acceptance of the null hypothesis will be very high, and while accepting the null hypothesis becoming high, you are going to make the second type 2 error more than the type 1 error, more than the previous one. So that means while you want to reduce one type of error, the type 2 error will automatically scaled up. So that's the problem. Now what you will do in general, we fix the alpha, we fix the type 1 error, and we want to find we actually find what will be the minimum value of beta, what is the test, what kind of test, uh, if we do that kind of test the beta will be minimized. That is called the most powerful test that I will introduce shortly. So another thing is that, and you see this alpha and beta will, for a simple test, suppose that let me give an example, x1 dot dot xn follows a normal distribution with mu and standard deviation 1. Now here we have to test whether the value of mu is 0 or not. Then this is my, suppose this is my hypothesis. So null hypothesis is mu is 0, mu is 0, and my alternative hypothesis mu not equal to 0. Now you see that these probabilities generally depends on this mu. So alpha will be, alpha will depend on mu, that is the probability of type 1 error, it is probability of reject H0 when it is true. So beta also depend on, so here this is called, and this is called the size of the test, and beta mu, that is the probability of type 2 error, that is the probability of accept H0 when it is false or alternative hypothesis is true. So that is, we can write it in this way: beta mu is equal to 1, beta star mu is 1 minus beta mu, and what beta star mu denotes, that is reject H0 when it is false. You see, you note this statement, that reject H0 when it is false, that means it is the power of the test, that means how much means this is that we are going to reject the null hypothesis when it is false. So that means it denotes the power of the test, so it is called actually the power function. And so here let me, since it is not possible, since it is not possible to simultaneously to control errors of both kinds, it is suggested that one fixed up to certain level and other is minimized. That is power is maximized. So you see that we since the both is not possible to minimize simultaneously, we usually fix this first type of error, the size of the test. We fix the size of the test, and now we choose the test in such a way that this beta star mu, that the power become maximized. So that is called the most powerful test. So that is called most powerful test. So in the next lecture I will give you the definition of the most powerful test, and how to I will introduce how to do the how to find the what is the way to find the most powerful test. And I will also introduce a lemma called the Neyman-Pearson fundamental lemma, and that lemma is very helpful for finding the most powerful test. And that's it. So that's all for today's lecture.